So 7.6 has two big concepts that we're going to be working through. The first one is going to talk about elementary power series. And these elementary power series are listed up here on the top of these notes. And we're going to talk about how we can use these to generate other series, use them to manipulate to find more complicated variations of these functions. We're going to do some practice problems with recognizing if a series is actually a manipulation of one of these series. And then we're going to lead into our second big topic for today, which is the alternating series test for convergence, which is going to be the third test that we have learned so far this semester. So we learned the nth term test, we learned the geometric series test, and then after today, you can add the alternating series test to that list. So that's just sort of an overview of where we are going today. Something I want to point out, a couple of things actually, that you need to memorize or you need to know these four power series. And actually, I'm going to add one to the bottom. I'm going to add the natural log of x plus 1, which is also one we have talked about. I'm going to add that really quickly. There we go. I wanted to make sure that I added natural log of x plus 1 because sometimes that version is actually going to be more helpful. And these series, we actually discovered these elementary power series in different sections. So we discovered sine and cosine series when we were exploring Maclaurin series. We looked over and discovered and had this giant aha moment when we found e to the x by analyzing the derivatives in the geometric power series section. We also came up with the natural log of x in that geometric power series section as well. So all 4.5, since this is really just a manipulation of this one, all four of these elementary power series are ones that we have looked at, discovered, figured out where they came from. And at this point, I'm just telling you, you need to commit these to memory. You need to be able to see a series and identify, ooh, that looks an awful lot like sine. And that's just what the point I really want to make at the beginning here. So let's actually stop and look at some examples using these power series. So here on number 1, the directions say use elementary power series for each of the following functions. Show the first 4 terms and the general term. So on number 1, we're obviously going to use the power series for sine of x. So we're going to use, I guess I shouldn't have scrolled so far up. We're going to use this power series. Woohoo! We're going to use this power series up here. The only difference is everywhere that there is an x in that power series, we're going to substitute in x squared, right? That's what's happening here. The only manipulation is that x is becoming x squared. So let's go ahead and write that out. And notice the directions do not ask you to write this using sigma notation, so you don't have to. And I'm going to choose, just since there's such limited space here, I'm going to choose not to write it out using sigma notation. So sine of x squared is going to be, well, what's the first term in the sine function? It's x. So instead of it being x, it's going to be x squared. That's coming from this term. Minus, well, normally x to the third over 3 factorial, but now it's going to be x squared to the third over 3 factorial. Plus, normally it's x to the 5th, but now it's going to be x squared to the 5th over 5 factorial. Minus x squared to the 7th over 7 factorial plus dot, dot, dot. I'm out of space here, so let's go ahead and look at the general term. I'm going to make that fit down here. So, whoops, I don't need another dot, dot, dot. So plus the general term, which is negative 1 to the n. And normally it's x to the 2n plus 1, but I'm really going to be saying x squared to the 2n plus 1 all over 2n plus 1 quantity factorial plus dot, dot, dot. So I'm going to go ahead and zoom in and clean this up a little bit, and then we're going to talk about how we could choose to simplify this to make it a little bit easier to look at. Okay, I think that is much easier to read. And I do want to point out that this could be simplified, right? We could definitely simplify this a bit, especially the general term. And if you're not asked to do that, you don't have to, and there's always a risk in doing that, which may or may not be worthwhile. But I want you to see what this would look like if I simplified it. So this would really just be x squared minus x to the 6th. Ooh, let's make that look more like an exponent. X to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. And then I'm going to simplify my general term, negative 1 to the n times x to the 4n plus 2 all over 2n plus 1 factorial plus dot, dot, dot. So simplifying this, if I was asked more questions about this series, I would probably want it simplified. If I'm not asked to do any more with it, then I'm probably not going to simplify it because, again, simplifying it puts me at risk for making an algebraic mistake that I don't want to lose a point for. So why don't you go ahead and pause the video and use the same idea for cosine of the square root of x, and go ahead and look up and use the cosine series on the top of this page. So the first term in cosine is 1 minus normally x squared over 2 factorial. So this is going to be x to the 1/2 squared over 2 factorial. You can leave this as square roots. That's totally fine. I just prefer, especially if I'm eventually going to simplify, I really prefer to have things as fractional exponents. So plus x to the 1/2 to the 4th power over 4 factorial minus x to the 1/2 to the 6th over 6 factorial plus dot, 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 plus our general term, which would be negative 1 to the n x to the 1/2 to the 2n all over 2n quantity factorial plus dot, dot, dot. Check and make sure that you're using appropriate notation with your ellipses. And I'm going to clean this up. Again, you do not have to do this, but x to the 1/2 squared is just x over 2 factorial plus x squared over 4 factorial minus x to the 3rd over 6 factorial plus dot, dot, dot. Get our general term in here, negative 1 to the n, x to the n over 2n factorial. And I want you to notice that even though this was cosine, and if you look up topic cosine, originally the cosine series has all exponents that are even, right? X squared, x to the 4th, x to the 6th. All that we did was manipulate cosine just slightly, and now we have x squared, x to the 3rd. So just because it starts with only having even exponents doesn't mean that we can't manipulate cosine in some way to look different. And I really want you to notice that as we move into possibly recognizing an elementary series that is already written out and trying to figure out what that original function is. Let's go ahead and look at number 3 again. I encourage you to pause the video and try number 3 on your own. So in red here, I have written our power series for e to the x. So for x e to the x, really all I have to do, is multiply that entire series, everything on both sides, by x. So x e to the x, and you could leave this as x times all of this rewritten. I'm going to write it a little bit nicer than that. So this would give me, instead of my first term being 1, my first term is going to be x plus x squared plus x to the 3rd over 2 factorial plus x to the 4th over 3 factorial plus dot, dot, dot. And what is this going to change to? This is going to become x to the n plus 1 over n factorial plus dot, dot, dot. So just a simple manipulation, multiplying the series a bit by, not a bit, multiplying the entire series by x, each individual term, including the general term, gives us our new power series. So number 4 gives us 1 over x, and I don't know about you, but by now my brain is trained that when I see 1 over x, it makes me think of natural log of x. But what is that real relationship? The relationship is that 1 over x is just the derivative of natural log of x. Whoops, let's not move my screen around. So this is really just the derivative of natural log of x. And we know this, we learned this a long time ago. How does that help us now? Well, we know the series for natural log of x. So what we can actually say is that, I'm going to move this a little bit, there we go, 1 over x is going to actually be the derivative of the series that we know for natural log of x. Well, looking up on your paper, that series is the first term x minus 1 minus x minus 1 quantity squared over 2 plus x minus 1 to the third over 3 minus x minus 1 to the fourth over 4 plus dot, dot, dot. I'm going to get my general term in here, x minus 1 to the n over n plus dot, dot, dot. Now, it is important, again, to have that series notation, and we are going to, ooh, what did I forget? I forgot that this is alternating, so I should have a negative 1 to the n in front, negative 1 to the n minus 1. Let me rewrite that general term. That looks much better. So now that I have this, I can take the derivative of each term with respect to x. So now I can say that this is equal to x minus 1, the derivative of that is just going to be 1, minus, this is going to be 2 times the quantity x minus 1 over 2, plus 3, right, we're just using the power rule here, times x minus 1 squared over 3, minus 4 times x minus 1 to the third over 4, plus, there's no n in my alternating term, so when I take the derivative, that's just a scalar that's in front, minus 1. But x minus 1 to the power of n is going to become n times x minus 1 to the power of n minus 1, all over n plus dot, dot, dot. And then this clearly is going to simplify 1 minus x minus 1 plus x minus 1 squared minus x minus 1 to the third plus dot, 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 plus my general term. Woohoo. And then that general term is going to be x minus 1 to the n minus 1. So cleaning that up really does make it a little bit more clear that this series is more simplified than the natural log series. Now, I also do want to point out that number 4 could have been done if the directions did not tell us that we had to use an elementary series. Number 4 could have been done in the geometric series section. This could be written as a geometric power series. And I'm just going to make a note of this because if you were just asked to represent 1 over x using a series, you could write this geometrically as 1 over 1 minus x, right? So you could identify your a, you could identify your r, not negative 1, 1 minus x. And after identifying your a and your r, you would actually get the exact same result with the exception of in our natural log version, we had x minus 1 instead of 1 minus x. But either way, we're getting the exact same power series. And I think that's really important to stop and note. Different strategies will work on different problems. And you need to pay attention to the directions, but you also need to really think through big picture, all the things that we have learned in this unit when you're thinking through a series. All right, why don't you go ahead and pause the video and work through number 5 on your own. So for number 5, I rewrote the series for natural log of x plus 1 up there. And then I rewrote the integral with that series substituted in. And then I took the antiderivative, and I didn't simplify yet because I wanted you to sort of stop and see. And we're evaluating this antiderivative from 0 to t. And actually, I wanted to show you one more thing. I want to do this part in a different color. We are integrating over bounds, so I don't need a c, but if I didn't have bounds here, I would need to include a plus c somewhere, and I need to make sure I still have a plus dot, dot, dot at the end. So typically if that happens, I'm going to throw my plus c in the front. But this is a definite integral, not an indefinite integral, so we don't have to worry about that. Now, we can directly substitute in and change all of our x's to t's and simplify as much as we can. And that would get us here. So pause the video, make sure that you got that. Make sure that you substituted t back in and make sure that you do not have a constant of integration. Now we're going to look at a series that is already given and see if we can identify from that series the elementary series that it is a manipulation of. So I recommend that you have your elementary series nearby so that you can look at them, and I'm going to try and help you think through each of these 4 problems remaining on the front of these notes. And I zoomed out a little bit so that I can really kind of give you some tips for thinking through this on your own. Now, some of you may look at any given problem and just immediately be able to figure out what that series is representing, but I'm going to pretend like that's not true and that you may need a little bit of help. And I'm going to try and help you kind of process through what is going on here. So for number 6, what I'm noticing, and they're specifically telling me that I'm going to use an elementary series. So what am I noticing? First of all, I notice that it's alternating. The next thing that I notice, besides that it's alternating, is that there aren't any factorials. So when I'm looking at my elementary functions, up top, sine, cosine, e, natural log, the only one that doesn't involve factorials is natural log of x. So looking at this actually, now that I think about it, looks an awful lot like natural log of x. In fact, the numerators are identical to the numerators in the elementary series for natural log of x. So now that I identified which one it is, I just need to identify what's the difference between the function or the series that I have in the natural log series. Well, the difference is in the denominators. And what's there that's not there before? It's got some extra. Number 6 is so extra. And what's extra? There's an x in the denominator that isn't in the original function. So we can say that number 6 is actually just natural log of x divided by x. And we don't need to write it out as a series because it's asking us to identify or write each as a function. All right, let's go ahead and look at number 7. Now, number 7, I'm going to start by looking at the same thing. So the first thing that I notice is that it's alternating. The second thing that I notice is that all of the exponents are even. Then I'm going to look at the denominators. The denominators, denom, are factorials, but I want you to notice not just that they're factorials, but they're all of them, right? 1, 2, 3, 4. We're not alternating. We don't just have even or odd factorials. So if you look at sine typically, or just sine of x, has odd factorials only. Cosine of x has even factorials only. E to the x has both. So my gut is going to tell me either I'm doing some sort of combination of adding sine and cosine, or maybe this is just e to the x. So I'm going to look at e to the x, and I'm going to see how could this maybe be some manipulation of e. So right now I'm asking myself, is this some manipulation of e to the x? So how could I do this? What's different here? Well, first of all, e to the x goes 1 plus x squared over 2 factorial plus x to the third over 3 factorial. So definitely my denominators are staying the same, but I have some numerator changes happening here. It starts with 1, so I don't have any issues there. So it looks like this is maybe e to the x, but instead of it being x, it's x squared. So now I've managed that. The only thing I haven't taken care of yet is, wait a second, e to the x isn't alternating, and this is. So how could I manipulate this to be alternating? I could make it a negative x squared. Ooh, I put that negative in the wrong spot. I can make it a negative x squared. So let's see, e to the negative x squared. That would make the sign alternate. That would also make the numerators, so remember, you're plugging negative x squared into your normal e to the x function, and you can go ahead and pause the video and test this out if you don't believe me, or even just test it out for your own sanity to make sure that this does in fact work. Number 7 is e to the negative x squared. And again, for some of you, these are going to pop out right away, and for some of you, you really need to be asking yourselves these questions and noticing what's the same and what's different. For 8 and 9, it says find the exact value of the series using an elementary series. So again, when I look at number 8, I'm noticing that it's alternating. I'm noticing that there's no factorials. Those two things, and even just the no factorials, is sending me to think that this is natural log. And if this is natural log, what is different about this and natural log? Well, there's no x. What is in the place where x would normally be? E. So this is actually the series for natural log of e, which we know is equal to 1, but you could leave that as natural log of e because it's just asking you what that series is. And then last but not least for our analyzing of these series, we're going to look at number 9. Number 9. So first thing I'm noticing is that the factorials are only odd. My factorials are odd, and I do have them. My exponents are odd. Only odd exponents. So odd exponents, odd factorials. This is making me, my gut is telling me, is this somehow related to sine? And this is related to sine. So when I'm looking up at sine, first of all, sine usually goes x minus x to the third over 3 factorial. How is this different here? Well, there's no first term. There's no term that's just x. And what is in the place where x is, the thing that's in the place where x is 2. So this actually looks a whole lot like sine of 2. Except if I substituted 2 into my sine function, there would be a 2 in the front, right? That means since that 2 is not there, this is actually sine of 2 minus 2. That's why there's no 2 in the front of this series. So feel free, pause this video, rewind it, make sure you really understand how I'm getting to these different elementary series and back to their original functions. And write down any questions that you have. This is something that you will get better at the more you practice it. And now we are going to move on to the alternating series test. As promised, we are going to learn now our third test for convergence. So we learned the nth term test for divergence, which means that if you take the limit as n approaches infinity of a series, and that limit is anything besides 0, that series will diverge. We learned the geometric series test, which we have been using a ton, including with power series, to talk about how the absolute value of our ratio needs to be less than 1 to show that it converges. And now we are going to talk about our third test for convergence, which specifically has to do with alternating series. So let's first just talk briefly about what an alternating series is. And an alternating series is a series that does just that. It's alternating in sign. Positive, negative, positive, negatives. The terms individually are alternating in sign. So you can see that could be written in either of these forms here. But they are alternating between positive and negative terms. Let's look at a geometric example of how an alternating series may behave. And let's analyze that a little bit analytically. So this series here, from n equals 1 to infinity of negative 1 to the n of 1 over n. Let's go ahead and let's look at the first few terms here. So if I plug in 1, I would get that my first term is negative 1. If I plug in 2, I would get that my second term is 1/2, minus 1/3, plus 1/4, minus 1/5, plus 1/6, minus, etc. It's going to go on and on and on in that manner. Now I want you to think about, ignoring the fact that we're alternating in sign, I want you to think about what's happening to each term. Each term is getting smaller, right? So I'm just going to say that you should know that each term, the terms are getting smaller. And I guess I should say the absolute value, right? We're not talking about, technically they're alternating between bigger and smaller because it's an alternating series. However, if you just think about the absolute value, so the first term being 1, the second being 2, the third being 3, each of these terms is getting smaller. So this is a decreasing series other than the fact that it is obviously alternating, but thinking about the behavior of the terms. So how could you describe the behavior of the terms? You could say that it's decreasing in absolute value. Each term is decreasing in absolute value. So what that means is I'm starting with negative 1 and then I'm adding 1/2. Where would I be there? I would be at negative 1/2. Then I'm subtracting 1/3. Then I'm adding 1/4. Then I'm subtracting 1/5. Each time I'm I'm alternating between adding and subtracting something smaller. So it does seem to make sense here that we will have a finite sum because we're never going to get above -1 in this particular series. Now let's extend on this and actually talk about the alternating series test for convergence. And most important word, well, two really important words here, alternating and convergence. So in order to use this test, you have to be talking about a series that's alternating, and you have to be talking, and you can only conclude convergence. So if the requirements are not met, we have to move on to another test, just like the nth term test. So you can either conclude that an alternate series converges using this test, or you can conclude that you need to go back and use a different test, which may be a test that we have not yet learned. So if an alternating series meets these two requirements below, then we can conclude that that alternating series converges. So what are these two requirements? And actually, there is a typo here. There should be absolute value symbols around those two terms. Not that those look like absolute value symbols, but the two requirements are, first, that the absolute value of the terms are decreasing. Like in the example that we just talked about, if you ignore the fact that it's alternating, the terms actually need to be getting smaller. You can show that by simply showing that the terms are getting smaller. You can also look at the derivative if you're really not sure to see if it's decreasing. And then the other thing we need to show is that the limit as n, two typos here, shame on me, as n approaches infinity of a sub n needs to be equal to 0. So if a series is alternating and both conditions, which you must show, both conditions are met, then you can conclude that your series converges by the alternating series test. So let's go ahead and look through some examples, work through some examples together, and then we will be done with Unit 7 content. All right, looking at number 1. Actually, let's zoom in a little bit. Much better. Looking at number 1, the first thing, I actually like to show the limit work first, and the reason being, if the limit is not equal to 0, then this diverges by NTT. So I typically will show the limit work first, and that's not true of everybody, but I like to show that factor. Also, notice that it says the limit as n approaches infinity of a sub n. This is the a sub n part. If you look back up at how we're defining this, a sub n is defined to not be the alternating part, to just be the term. You don't need to show the limit of the alternating part. And we've talked about this before in earlier sections because you're really taking the limit of the product of those two things. So if the limit of a sub n is 0 and you multiply that limit by -1 to the n, you're still going to get a limit that's 0. So the limit as n approaches infinity of 1 over n plus 1 equals 0. If it didn't equal 0, then right now I would say, therefore, that's not 0 and it diverges by NTT. But this limit does equal 0, so I have officially checked off one of the two criteria that I need to show in order to use the alternating series test. Also, it needs to be alternating, which it clearly is. You don't need to state that it's alternating. Now I want to go ahead and look at the absolute value of the terms. So ignoring the alternating part, 1/2 is the first term, 1/3 is the second term. Again, I'm ignoring 1/4. I'm ignoring the sign. I'm just looking at the individual terms. What's happening to the terms? 1/2 and then 1/3 and then 1/4 and 1/5. They are getting smaller. So you can say that a sub n plus 1 is less than or equal to a sub n. Therefore, the series converges by AST. So first condition, second condition, therefore it converges by AST. Now you don't have to prove that 1/2 is greater than 1/3 or any real full-on proof that the terms are getting smaller. You just need to show that they are getting smaller. And I typically show that by listing them out. Again, you could also show the derivative of 1 over n plus 1. You could show that that derivative is negative, which would also indicate that the terms are decreasing in absolute value. So why don't we go ahead and look at number 2. All right, number 5. Let's go ahead and first look at the limit. So the limit, again, alternating, so I can use the alternating series test. The limit as n approaches infinity of n plus 1 over n, that limit is equal to, what is that limit? That limit is equal to 1. But wait a second. That limit is equal to 1. That means we can't use AST. But we could use NTT. So the limit as n approaches infinity of -1 to the n plus 1 times n plus 1 over n, this limit is not going to be equal to 0. Therefore, instead of using AST, even though this is in fact an alternating series, instead of using AST, therefore this diverges by NTT. So this diverges by NTT. AST does not apply on this particular problem. I encourage you to pause the video and work on 3 through 6 on your own, and then unpause the video and see how you did. Okay, so number 3, that limit as n approaches infinity of n over n squared plus 1, the bottom is growing faster than the numerator, so that limit is 0, 1/2, 2/5, 3/10. These are getting smaller, so a sub n is less than or equal to a sub n plus 1 is less than or equal to a sub n. You could also write in words that the terms are decreasing in absolute value. Therefore, this series converges by AST. So on number 4, I'm going to take the limit, and number 4 is one where you could list out the terms and show that it's decreasing. Obviously, the denominator is getting bigger, even though it's getting bigger at sort of a weird rate, right? N to the power of 5 over 2. The other thing you can do, and this is a great example where I'm going to show you how you could use the derivative. So I'm going to say let f of x equal 1 over x to the 5 over 2. That means that f prime of x is negative 5 over 2 times x to the negative 7 over 2. Since it is negative, therefore f is decreasing, which allows you to then say that a sub n plus 1 is less than or equal to a sub n. You could do what we have been doing, what we did on number 1 and number 3 as well. So we have shown our 2 conditions are true, so we can say that this converges by AST. Go ahead and work on 5 and 6. And number 6 is going to be a little challenging because it's not currently written using sigma notation, and I do recommend that you do that first. All right, number 5, the limit as n approaches infinity of 1 over 3 to the n is 0. Looking at the terms, 1/3, 1/9, 1/27, those are decreasing. Therefore, this converges by AST. And let's go ahead and first write the rule for number 6. So let's identify, and I'm going to use sigma notation. Let's go ahead and identify this rule here. So let's start from 0 to infinity. What's happening here? So our numerators are just multiplying by 2. Our numerators are multiplying by 2. What's happening in our denominators? So actually, let's make this n equals 1 instead of n equals 0. Our numerators are multiplying by 2. Our denominators are, if I started with 1 and then I'm at 5, then 6, our denominators are adding 4. So n plus 4. Plus, let us not forget the whole purpose of the test we're looking at right now is that it's alternating. Our first term is negative, so we also need a -1 to the power of n. So we have an alternating series, and looking at those terms, I can see sort of what's going on here. And you may have actually noticed first that these terms are actually increasing. The terms are increasing 2/5, and then at some point I get to 8/8. Well, that's 1. Definitely our terms are not decreasing in absolute value. So AST would be inconclusive here, which means that we can't actually use AST on this particular problem. So it's not geometric. The only other test that we know of as of right now is the nth term test. So let's go ahead and look at the limit. I also want to point out, if you didn't notice that the terms were increasing in absolute value, your gut should have been to take the limit first anyways. So -1 to the n times 2 over n plus 4. The limit of this is 2. 2 times something that's alternating, so 2, -2, 2, -2. This limit is not going to be 0. this limit is not going to be 0. That means that this diverges by the nth term test. So it is often the case that you can use NTT when AST doesn't work, which is why I always pointed out it's good to start with the limit work first. So let's recap the key ideas in this section. The first thing that we talked about had to do with elementary series. Knowing those 4 elementary series, being able to identify and manipulate them, being able to identify when something is already a manipulation of them. And then the second key part of these notes was the alternating series test for convergence, showing both that the limit as n approaches infinity of a sub n is 0 and that the terms are decreasing in absolute value in order to use that test. Make sure you write down any questions that you have, and I look forward to supporting you on this in class. Thanks for listening.